Next, we're going to see how to prove some of our derivative formulas for the inverse trig functions and the inverse exponential functions, which we normally call log functions. So we're going to be looking at inverse functions. So it's going to help to know, well, what is the definition? How do we actually define what an inverse function is? So we have it here. We have some function f, and what we're defining here is its inverse function, f inverse. And we use this notation. So when we write f inverse like this, that -1, this whole thing is just pure notation. So think of that as just all one piece of notation. So just kind of put a circle around it. That's just the whole name. That's the whole name of a function, f inverse. So it's tempting. You see that -1 kind of where it looks like an exponent might be. It's not an exponent. In this notation and in this discussion, this -1 is not an exponent. It's just indicating that we're talking about a different function, the inverse function of f. So it's not an exponent, and inverse function, the inverse function evaluated at x does not equal 1 over f of x normally. Maybe some special cases where that's true, but in general, the inverse function evaluated at x does not equal the reciprocal of f of x. So it's not an exponent. So just kind of get that out of the way right away. All right, so what is an inverse function? Well, here's the definition. So if y is equal to the inverse function evaluated at x, well, for this to be an inverse function, what has to happen then? So if and only if, so this is true, if and only if x is equal to our original function f evaluated at y. All right, so that's the definition. Probably to put a little context in this, it's helpful to consider the cancellation properties. So the cancellation properties here probably make a little bit more sense in terms of what this inverse function is actually doing. So there's two of them based on where we apply the inverse function. So let's look at the first one here. If we have input x and we plug it into our function f, and then we take that result and plug it into the inverse function, we get x back. So effectively what's happening here is inverse f cancels with our original function f. So they just kind of cancel out. And it works the other way as well. So if we take some number x, plug it into the inverse function, and then take that result and plug it into the original function f, well, there, inverse f and f cancel again, and we're left with our original input. So you can kind of think of it like a machine here. We have our input x is what we're starting with. And let's look at the context of this first cancellation property. We plug it into function f. That gives us out f of x. And then we turn around, take this result, plug it into the inverse function, so inverse of f. And what happens is the inverse function of f effectively undoes what function f did, and it gives us back takes us back to where we started. So we started with x, plugged it into function f, that gave us something, took that result, plugged it into the inverse function of f, and we're back where we started. We're back with our original input. So effectively what's going on here, f inverse effectively is an undo. You can kind of think of it as like an undo function. It undoes what function f did to your input. Or You can think of them as, or you can think of this as just it cancels out. So it's how you would cancel out. If you had function f, it's the function that allows you to cancel off that function f. So we're going to use this definition, though, in how we prove the derivative of our inverse trig functions.